So let us continue our study of the properties of Laplace transforms. Now in this lecture I will make this assumption. So this is an assumption for this lecture. So we assume that our functions ft will be piecewise continuous on the interval 0 infinity and of exponential order. So we remember from our sufficient conditions for the existence of Laplace transforms that if a function is piecewise continuous on this interval 0 infinity with 0 included, and if it is of exponential order, then the Laplace transform exists. So this assumption will make many of our technical points for the analysis of integrals easier, and so we have made this simplifying assumptions. So most of the functions that we will see in this course will be of this type, so we are not losing too much from this assumption. So let us see our first property. So the first property is behavior of Laplace transforms at s equal to infinity. So this, let me write this as a theorem. So if we write fs to be the Laplace transform of the function ft, then the limit as s goes to plus infinity of fs is 0. So let's see a proof for this statement. So note that it is sufficient to show that the limit as s goes to plus infinity of the modulus of fs is equal to 0. This is due to the squeeze theorem for limits. So here we have minus mod of fs is less than or equal to fs is less than or equal to mod of fs, and so if the limit of modulus of fs goes to 0, then this part goes to 0 as s goes to plus infinity, and this part also goes to 0 as s goes to plus infinity. So the middle one also goes to 0 as s goes to plus infinity. So this is this application of squeeze theorem. So now, by definition of the modulus of our improper Riemann integral, so this is simply the definition of the Laplace transform of ft. So this is just fs. Now because this, we have assumed that ft is of exponential order, this limit exists, so we can put it inside. So we can put the absolute value of this term inside the limit as r goes to infinity. So we can write limit as r goes to infinity modulus of the integral 0 to r ft exponential minus st dt. Now we know that because our ft is of exponential order, so suppose that there exist constants m, alpha and t naught such that modulus of ft is less than or equal to m e to the power alpha t for all t in the region t greater than or equal to t naught. This is just the exponential order property of this function ft. So now we can evaluate this limit as r goes to infinity, and we have already seen it that it equals m over s minus alpha. So one can solve directly So the limit as r goes to infinity, modulus of integral ft exponential minus st dt is in fact less than or equal to m over s minus alpha. So this is for s greater than alpha. So now we get that our limit as s tends to plus infinity of modulus of fs. So we have that this is equal to the limit as s goes to plus infinity, limit r goes to plus infinity modulus of, sorry, so this should be r here, 0 to r ft exponential minus st dt, and now we know that this is less than or equal to m over s minus alpha for all s greater than alpha. With the limit s plus infinity, this is simply 0. So therefore we have shown that the limit as s goes to plus infinity modulus of fs is 0. So again, by this application of the squeeze theorem that I said before, this is also equal to 0. So for any function which is piecewise continuous and of exponential order, we have that the Laplace transform must go to 0 as s tends to plus infinity. Now the second property is the Laplace transform formula for the Laplace transform of t ft. So this is a new function gt. Note that if ft is chosen to be piecewise continuous and of exponential order, if ft is piecewise continuous, I'll just write PWC for short, and of exponential order, then TFT is also piecewise continuous and of exponential order. So we know that from the sufficient condition of Laplace transforms that the Laplace transform of GT exists, and now we will try to give a formula in terms of the Laplace transform of ft. So this theorem states that the Laplace transform GS, so if we write GS as the Laplace transform of GT, then GS is given by the formula minus the derivative of the Laplace transform of Fs, where capital Fs, this is capital Fs, is the Laplace transform of Ft. So let us see how we can show this. So remember that our Laplace transform, so capital GS, which is the Laplace transform of GT, is given by 0 to infinity TFT exponential minus st dt. Now we have that capital F of S, which is the Laplace transform of Ft, is by definition 0 to infinity Ft exponential minus st dt. Now if we write d over ds of Fs, the derivative of Fs, then this is d over ds of this integral 0 to infinity Ft exponential minus st dt. Now if we can make this integral sign and the derivative, if we can interchange these two operations, so suppose that we can interchange these two operations, d over ds of Ft exponential minus st, so this is a partial derivative now, dt. if this is true, then our result is immediate, because we have this partial derivative is nothing but minus t ft exponential minus st dt. So this implies that the integral of ft exponential minus st dt is minus the derivative of fs, and this is the left hand side is gs. Now the only thing is to show that this operation, the interchange of the two operations of derivative and integral is allowed, and in fact by our standing assumptions on the function ft, which we have assumed that it is piecewise continuous and of exponential order, this interchange of integral and derivatives is in fact allowed. But for the moment we will not go into the details. If time permits, I will write down a sufficient condition under which integral and derivatives can be interchanged. Note that one can easily give counterexample where interchange of integral and derivative is not allowed. Interchange of integral and derivative fails. So a standard example is this function fy given by integral 0 to infinity sine of xy over x dx. Note that we are integrating over x, and so we are left with a function of y. Now if you write the integral with the partial derivative with respect to y of sine xy over x dx, then this is simply the integral 0 to infinity cos of xy dx, and we know that for any value of y this integral does not exist for any y. This is a divergent integral, an improper Riemann integral which does not exist. So if you take the derivative, partial derivative inside, then the integral does not exist. However, we know that integral 0 to infinity sine xy over x dx, this can be rewritten as integral 0 to infinity sine u over u du. So here we have made the change u equal to yx, so du equals y times dx. So we get, from here we get, after this change of variables from x to u, we get sine u over, so we get this integral sine u over u du, and we will see later that this is in fact a convergent integral. It exists as an improper Riemann integral, and in fact one can show that this value is pi by 2, and we will show this later on using Laplace transform techniques. So we say that we cannot always interchange the integral and derivative sign, but there are sufficient conditions under which you can do this, and I will write them later on. And you will see that if ft is a function of exponential order and if it is piecewise continuous on 0 infinity, then it will satisfy that sufficient condition under which you can interchange the derivative and integral signs. So which says that this is the multiplication by t to the power n. So we try to compute the Laplace transform of t to the power n ft in terms of the Laplace transform of ft itself, and the theorem here states that Laplace transform of t to the power n ft at s is minus 1 to the power n. So here n is a positive integer, so minus 1 to the power n, the nth derivative dn over dsn of fs. So if n equal to 1, we have already seen that this is true because you will only have minus 1 and the derivative of fs, and one can generalize this using an induction technique. So proof is by induction on the power n, on the exponent n, and I will leave this as an exercise. So is an exercise for you. Check this formula. You can assume that when ft is of exponential order and piecewise continuous, then you can interchange the integral and derivative for the Laplace transforms. So let us see an example. So first let's consider the Laplace transform of t sin t. So this is from our previous property, minus derivative of the Laplace transform of sin t, and this is the, we know already what it is. So at s we have 1 over s square plus 1. So you get minus, and then you have minus 1 over s square plus 1 whole square, and then 2s. So you get 2s over s square plus 1 whole square, and this is valid for s greater than 0. So if you multiply by t, you can differentiate once and put a minus sign at the front, and you get the formula for the Laplace transform of t times that function.